and start the lecture. Well, let me share the link with the rest of the group to the recording of the lecture. It should be available right about now, probably. Well, that would have been the case if YouTube hadn't died. So, uh, today I wanted to share with you information on what are the drivers in Blender, how we can use them to make our lives easier for animation, and how to use basically animation, how to approach it, how can we use deformations of the object, how to make animations that allow us to easily deform the meshes during animation time, and how to control animation, make it more snappy, make it more impactful, make it more dynamic, etc. And by the end of the lecture, I think we will also touch a bit on the physics, the physics engine of the Blender, touch a little bit of closed materials, a little bit of just rigid bodies, and what you can achieve with them. Uh, I think that it will be a great ground for uh, geometry nodes. So on the next lecture, the last one that I will be giving to you, you will have a quite good understanding of how to use of everything that you need to be comfortable using geometry nodes. So let me increase the scale of the interface so that you have a better view of what is happening. And okay, let's begin. First of all, I would try possibly to engage you in the lecture if you don't mind. So we have these two types of gears, a worm gear and a regular gear. Now, if I wanted to animate them, to make it so that when this gear rotates around its rotational axis, it also moves this gear. How would you do that? How would you approach it? Well, if you, yeah, all right. So what I would have tried if I were starting Blender like a few weeks ago. I would try to make a keyframe at the beginning of the timeline. Yeah, actually, let's talk a little bit about how animation works. All of the animation, no matter how complex it is basically a set of things called keyframes that tells where and how each object should be placed at each frame of the scene. So when we look at the Layouts tab of the Blender, we can see this timeline at the bottom. On this timeline, when we add some keyframes by pressing I on some fields, for example, on location or rotation, it will add a keyframe. In version 4.1, it is a letter K, because they reworked animation a little bit. So we added a keyframe with these arguments: x rotation on the axis x of 90 degrees, y 0 degrees, z 0 degrees, at the time frame 0, at the frame 0. But then let's move all the way to the end. You can do that by pressing Shift and arrow keys to the left or right to snap to the end or to the start or the end of the animation frame, which we can control there. So let's make a 100 frame animation and put at the end frame of this animation this gear. Let's rotate it on the y-axis, for example 360 degrees times 10. Okay, it can do times 10, so let's just rotate it 3060 degrees. So it's 10 revolutions around its main axis. Insert the keyframe. You can select all channels or inactive group. And let's move to the very beginning of the animation and press spacebar if you didn't unbind it to other thing. And we can see that it makes 10 revolutions as we wanted it to do. So it makes 10 revolutions. All right. So each of these gear moves for 10 sections each. What does it mean? It means that this gear should have also 10 teeth move one section. So the space between, how do we apply it to practice now? We know that this gear, each teeth of this gear makes 10 steps this way. Well, then we can make this gear rotate by 10 steps as well, because, well, that's how gears work. So each step of this gear will be the space between the teeth of this gear. So if we want to make 10 steps, we calculate the angle between two teeth and multiply it by 10. What is the angle between two teeth? Well, we take 3060 degrees and divide it by the number of the teeth, which is 1, 2, 3, 4, and this is a quarter of the gear, so it is 16 teeth. Well, if we want to calculate what we wanted to, 3060 divided by 16, we don't even need to open our calculators, because we can put all the math right here. So let's add a keyframe with 0 rotations there, and at the end we want to rotate our gear on the z-axis. So we put 3060 divided by the number of the gears and multiply it by how many steps we want it to make. Don't forget to insert a keyframe. And now, if everything works fine, as you see, it is not fine, because we didn't pay attention to the direction of the spin. So just put a minus in here, and well, someone forgot to insert a keyframe. Now that's better. And it is even synchronous. Well, looks good enough. But if I wanted to change this animation slightly. For example, if I wanted it to start slower and then pick up speed later, I would add an intermediate keyframe there so that it only makes 2 revolutions during these 48 frames and the rest 8 revolutions after that. So it starts slow, picks up speed later, but this gear is now asynchronous with this thing. It may be, now it is still very noticeable. But so if we want to make it more controllable, so that we can animate only one part and the rest of the mechanism follows its movement, we can use a thing that is called drivers. Well, basically what we did still holds. We still remember that each revolution of this gear causes one step of this gear. So let's clear all the keyframes and add a driver there. In this driver editor, we can select an object. Let's take this gear. Select some value of this object. In our case, it is rotation along the y-axis. We can even select the coordinate frame from which we want to take it. And it will read the value that we provided it. So in our case, it is the y rotation in automatic Euler mode in the world space. And it translates this value to the variable called var by default. And after that, we can do whatever we want with this value. We can put it in sinus, we can put it into power, but for now, we will be fine if we just divide it by 360 to make to calculate how many steps are driving worm gear made, and then multiply by how many degrees we want to rotate our drivable gear for basically each step. So now reconcile what the formula was. It was 360 degrees divided by 16 teeth, and well, that is it. So let's try that. Don't forget to put a minus in here. Now it should be working just fine. Yep, and what's even more interesting, that we can drive this thing by our own, and it will work with this gear just as we would expect. It is a very powerful tool, which you can use not only in hard surface animations, but in soft bodies animations. For example, when you are doing characters' elbows or knee pads, yeah. If you make an elbow, you will have some very strong artifacts where your elbow bends. So you can use an intermediate bone. Let's actually show it. Imagine that it is an arm. Reposition it to the 0 and add an armature that we have worked with on the previous lecture a bit. Make it in front so that we can see it all the time. Rotate 90 degrees and make it look like there should be an elbow there. Now, do you remember from the previous lecture how to assign the parent object to the bones, or to those 2 bones? Well, in that case, let me remind you. By selecting those two objects, you can use Ctrl P to assign automatic weights or just assign to each individual bones. We shall be just fine with automatic weights. And this way, we easily bend our object. So this is the type of artifact that I was talking about. The elbow is, if we look anatomically on what our elbow should look like, the bones still stretch to this point, and only here they make a joint. So the flesh and bones, the flesh and skin, should wrap around it kinda like that. We can kinda try to fix it with geometry by adding more loops there. For example, you can make a knife cut from here by the axis and make it go through by pressing C and add some geometry to this point. Define on the other way as well. Well, let's see how it behaves. Well, it is better, but still our elbow is stretched inwards when we don't want it to be stretched inwards. What we can do from here, we can make another bone clear its parent, so basically disconnect the bone. Actually, no, let's parent it back, but not connect it, and just keep offset, so that this bone we can move, and this bone moves with its parent. From here, we can see what kind of rotation it is. Let's go to the Euler and say that this X rotation will be half of the rotation of this bone. Let's select the proper bone. It is, I believe, bone 001. Yes. And we control X rotation. We want to control it with X rotation as well in the local space and just divide it by 2. Let's see what this does. It keeps our elbow bone rotated by half of what the other bone is making. Now if we were to just assign proper weight to this part of the bone, let's just do it automatically. And see how it behaves. Well, doesn't look as good. But with just a little bit of correction, it should be much better if we now go to the weight paint and paint it with absolute ones, paint this area. And probably fiddle around a bit with the weights, with the positioning of this bone. Alright, and for better testing, I propose that we can animate this bone. So once again, insert keyframe, and somewhere in the middle, bend it a little bit. And now, if we press play, it allows us to play everything. Now, if we move this bone a little bit around, well, I think you would agree that this result looks much better than what we had before. It looks like much more natural and behaves like you would expect an elbow would behave. Another thing that we can do with drivers, just to reiterate on how powerful it is, let's create a simple cube, bring it a little bit to the surface, play around with some modifiers, just subdivide it a little bit, add twist modifier, I believe. No, not twist. Then it should definitely be under deform. It is simple deform. Yes. Let's bend it on the x axis. Yeah, let it be x. And exclude this vertex group. Let's call it base. Okay, so it twists. I don't like from where it twists, so let's do it like that. Now it twists better. And add another modifier, another simple deform, to make it twist along the z-axis, so it can kind of rotate into both directions. All right. And let's throw in another subdivision modifier to smooth it out. Well, this gelatinous cube already has some character to him. We can even animate it to make it feel alive. But it would be much more easy to control its behavior not by controlling each individual modifier, but to have something that we can visualize more easily on the scene and control it more naturally. So let's create an empty object somewhere in front of this cube. Let's call it driver controller to keep everything in place, and add some drivers to it. So this thing tilts the top of the cube. So what we want to do now is to make it so that this cube looks at the proper height of this object. Now that you have seen how drivers work, I would ask you to help me make a proper driver for animating this cube, so that it looks with its top part to this empty object. Someone. At least show me that you are there. And yeah, well, that's good. Yeah. All right. So we using drivers, we can read the height of this empty, and and if we plug this driver into the angle here, we can control the tilt of the top of the cube. So if I want to make it tilted in such a way that it looks on this empty, let's start by actually creating a driver there. We can do that with Well, there was an option to do that, but let's do it the old-fashioned way. Add a driver and select an object. Well, our target is driver controller. Now, what we want to read from it is its height. It is its z coordinate. So we take z coordinate, z location. You can even take it from the local space. It already tells us what is the value of it. It is 2 now. Well, since we are working with the top of the cube, then its value is 2 on this height, and it should be 0 at this height. So what we want to do is to make our tilt 0 on the level of 2, make our tilt negative if we are looking there, and make our tilt positive if we are going there. So we can just slide this entire number line upwards by basically subtracting 2. So if we do that, let's subtract 2 from the value. Well, our cube is now perfectly straight, but if we move this up and down, it behaves exactly as we don't want it to. So let's come again back there and put a minus in front of the expression, and probably change this -2 to 2 because we wanted to put a negative sign in front of the whole thing. So now when we raise it up and lower it down, it tilts its head with accordance to this thing. But unfortunately, it only follows this empty for a little bit. But after that, when I move it higher and higher and higher, it starts to make backflips. Now it will be a little exercise in linear algebra and math. How would I do that so that so that this cube looks straight to this empty? Do you have any ideas? Yes. Yeah. Of this height, I believe, divided by this length. Well, let's see how it works. And if it works, then we are good. If not, then we would have to change something. .arc sign. Well, let me open a reference quickly. Well, it should be just a scene of this thing. Hold on a second. Let's open a console and see built-in function. Yeah, it should be in range from 1 to from -1 to 1, I believe. Yes. All right. So this value var, well, it would be a scene if we were taking arc sinus, which is the relation of the further side to the larger side of the right triangle. But calculating this, I don't remember how hypotenusa in English. Hypotenuse was that simple? All right. So if if we work with that, we need to calculate hypotenuse each step. What we can do instead of that, we can use tangent. We can use actually arctangent. By dividing this length by this length. And since this length is fixed and this length scales upwards, we should be just fine using tan here. And probably this +2 should go inside of it as well. Yep. Now when we tilt it down, it kind of follows. And if we tilt it up, it also kind of follows. But if we raise it all the way to the sky, it doesn't make backflips at least. So I would say that it is a good progress. We can even apply some restrictions on this value, but let's not dive so deep. Now let's do the same thing for the twist on the x axis, so that if we move it to the right and the left, it also follows the same thing. Well, would someone guide me through that? Yes. We have a twist there that allows us to, well, twist it on the z-axis. So we want to get an angle here that follows this empty around. Let's firstly move it so that it follows on the x-axis. Yes. Yep. Yeah. Firstly, we need to select the target. From what object we gather our information. Yes, we do that here on the object. We select the driver controller. Now we select what information we want to gather from it. In our case, it is X location. Do we want it to get from the local space or from world space? It can be world space if we keep our cube in place all the time. But if we want to move our cube, then actually let's see how it behaves now when we move it up and down here. It's well, okay. there was an issue there with this cube, with the first driver. It should be transform space, probably. No. Well, that's inconvenient. All right. Well, it's in theory at least should be local space, so that we take orientation from the origin of the our cube. Yes. So that we can take not the position not from the center of the world coordinates, but from the center of the cube. So yeah, take local space, and you see that its value right now is let's just open a window editor. That its value right now is 0.5. It goes into positive direction, and well, the x is now in positive direction. Yeah, it is fine. Let me just apply the scale to the empty. All right. So we have this value, which is the distance between the cube and which is which will be the distance between the cube and the empty. Now, how we do the rotation? Let's take a top projection. So we know this distance. It is our variable. How do we get basically this angle? Not this angle, but this angle. So it turns negative in this area. Let's try doing that. Yep. Atan should be fine. Well, it works a bit sharp at the moment. Well, that is because this distance that we have here is not 1, but actually, yeah. So we would want to divide this var by this length. We can either put this information into the driver to just hard-code it to 2.6 meters and even place a constraint on the empty so that its location is limited to the y of 2.6 so that we can't drag it from this distance. But what we also can do, we can get here another variable. So let's call this variable dx. Not dx, but delta x. The difference in x coordinate, and rename this variable accordingly. And here we can get another variable from the same object, but call it delta y. And as you have guessed, we take location of the y and divide delta x by delta y. Now it works better. Yep, good point. And well, that now we have an issue of the jumping cube when we cross the negative sign on the y-axis. that can easily be fixed if we use atom2. This function is basically identical to basic atom, but it takes two arguments and accounts for this very issue. So that when you go over the border, it makes the value also go into the further numbers of the angle. So it only flips here on the very negative value of y. And well, as you can see, we have our empty object that we can orient wherever we want. And if we put some texture, put some maybe cartoony eyes on our cube, unfortunately those eyes won't move, then it will be already a very nice cute character. So that is how you can use drivers for hard surface modeling, for moving gears, shafts, other parts, even for moving things like elbows in your models, and twisting different things. As you have seen in the driver, you can put mathematical functions and get some really incredible results with whatever your imagination can basically imagine. Now, it was 45 minutes of the lecture. Let's, I think, make a little break. Let's have 5 minutes break. While in the meantime, I will prepare a scene for the next part of our lecture. So, yeah. Yes, I hope so. I, yeah. Ah, well, we are living in a Polish university. We have a great opportunity to practice English, and since yeah, on recording it even makes sense. So I am taking the most advantage from what I do. All right. The break time is up. I hope that you can hear me well and everything is still fine. Please confirm it. All right. So the local frame and the world frame are very important when we are working with this thing. And this is how you actually differentiate with them. Local frame is the location and rotation that you see in this transform window. It can be either to the world point, or if you properly parent your object, so this empty is now parented to the cube. As you can see, it is now in the subfolder of the cube. Then its local coordinates are now calculated here from the origin of the cube. So that if I reset this to 0, you can see that it goes to the 0, not of the world, but of the parent object. And now I can move the cube. It moves its children with itself, and it tilts around its own axis. But if I were to change it to the world frame, it would get the x location from the world coordinates. So it would take this much location. And as you can see, our cube thinks that it's empty, its target is placed somewhere there. So this is the distance that our delta x that our cube tries to look into. Now, let's get back to the second part of the lecture. Animation. I have a ball, I have a plane. I want to make this ball bounce from the plane like you would expect a ball bounce from the plane. Let's place the ball in its initial position, place a keyframe there, and somewhere in the end, well, let's not go this far. Actually, no, let's go. And think that our ball should be somewhere there. Now, if I were to place some intermediate points, like on the fifth frame, place it somewhere there, in the middle. On the 25th frame, I would bring it down there. On the 75th frame, I would also bring it down there. Let's see how it looks. Well, that is definitely not bouncing. The issue is that we have our 5 keyframes, and the data between them, the location of the sphere on y and z axis, is interpolated smoothly by f-curve. To visualize it better, we can go from the timeline to the graph sheet and see how each value there looks. It is a very nice visualization. On the blue graph, we see the y, the z position, and on the green, we see our y position. So if you follow, it moves according with how we told it to. Yes. Now what we want to do there is to make this part sharper, so that it looks not like, so it's not this smooth, but in reality we would expect, since it is a graph of height, it should look something like whoop, whoop. So it should be a parabolic shape that gets inverted at the moment when we touch the ground. Let's try to do that. We can take the handle and change the type of the handle. By default, it is not F-curve, Bezier curve, which is basically, yes, F-curve in multiple dimensions. So let's go with, what should it be? Quadratic, I believe. And it changes interpolation mode for the following segment. So now, boom, at least this fall was pretty neat. Probably it should happen faster. So we can take, to do that, we can take those keyframes and just drag them along our graph view. Since on the x-axis, from left to right, we have our timeline. If we take this data and move it closer to the left, it will make our animation more fast, because we decrease the time for that part of the animation to happen. Boom. Now it falls like a rock. Make it, let's give it a little bit more time. 15 frames should be fine. So now 15 frames there, then 30 frames should be there, 45 here, and the last thing should be on the 6th frame. And let's go back to the timeline to just set that our animation ends on the 6th frame, 60th frame. Well, now let's fix this thing. We should change the easing time type, I believe, or should it be I am so sorry, I completely forgot about it. I feel that it should be quadratic, but it should be... Yes. We change the easing type from is in to is out, so that it basically mirrors the direction of this part. Now let's do the following for the next part. We make quadratic is in, which is automatically selected, quadratic, and is out. Now our ball is very bouncy. But it can be better. If some of you have attended some animation schools or maybe animation tutorials on YouTube, you probably should have seen these videos where you make incoming thing more stretched in, then as it moves faster, it stretches out even more, and when it touches the ground, it stays not as a perfect sphere, but as something squished to the ground, only for them to bounce back up, to regain its shape, and again convert into something more stretched as it moves faster further. With Blender, we can easily do that with the help of the thing called shape keys. First of all, our object should have a basis. It is a basic position, the rest position of our object. Then for the each next key, each next shape key, we can deform our object somehow. For example, let's make it all stretched up by grabbing this thing, using a proportional editing, make it smoother to the top, and stretch it out a bit to the front as well, and shrink it a bit. That is our key one. We edited it when we selected key one. Now if we change its value from 0 to 1, our object changes its shape from 0 to 1, from the 0 effect of the first shape key to absolute effect of the first shape key. Now let's create another one. Reset this one to 0, select it, and make a squished position of the ball. Just take the bottom of it, squish it in, and make it a little bit wider so that we can feel that it is squished. Let's see how that looks. Well, as you would expect, as a squished ball. So now we have a stretch of the ball, and squish of the ball. First of all, when we start moving there, we have very little speed. Most of our speed comes from the moving closer to the ground. So at this point, we should be the most stretched. So let's put its value to 1, and at the beginning, we should be the least stretched. So 0. And after that, we should, at the moment when we touch the ground, which is 15th frame, we should go from stretched to squished. And before that, our squish should be 0. Now, to mirror it, we can basically, let's firstly hide all the graphs for the orientation of the object. To mirror this thing, we can select these points because those points are treated as objects, basically as objects on your scene. You can work with them just like that. You can select them, you can scale them on different axes, on X, on Y. You can grab them and move along one axis or another, and you can duplicate them. And after you duplicate them, you can scale them to -1 to reverse the order. If you scale them by -1 on the x-axis, you get the reverse order of this entire thing. So let's duplicate it, drag it somewhere to the right, scale it by x -1, and bring it back in. Now we should correct a little bit the top position. So Z should be there. And we get a very subtle squish that gives us a very good look on the physics of the ball. Now let's hide the thing, duplicate it to the right, and let's see how it looks. Well, it's definitely not as good as it could have been, but to make it better, when our ball stretches, it should stretch in the direction of the movement. So let's orient our ball in the direction of the movement. It goes from this orientation to about this orientation. Then on 15th frame, it is perfectly vertical. And after that, let's just hide the location graphs, the key value graphs, and leave only X rotation. So this value. It is not very convenient to work with such high values as you may have imagined. To make it more easy for us, we can press the normalize button, and it will basically normalize the values from -1 to 1. And there should be a way to scroll into it somehow, so that I don't scroll both values at the same time. Well, maybe not today. Yeah. Yeah. Unfortunately, no. Uh... Yep. There should be a way. There has to be a way, but let's not waste our time on it. So we can just do the same as we did before. Place our cursor to the 15th frame, duplicate the thing, move it to the right, scale it by x to the -1, and bring it back to where we want it to be on the 15th frame. Now, well, there's an issue, because this ball now gets rotated into the same direction as it was rotated before. Can you tell me why that happened? Because we mirrored the graph below there. Why isn't our ball's rotation not mirrored? Why is our ball rotation not mirrored? And what does that mean? Exactly. The height here on this graph is the rotation of the object. So if our graph is very low, our object rotated to the left. And if you go here upwards, we go to the 0, and then we come back low to the place where our object was rotated to the left. So let's select our guideline keyframes and scale them by the y-axis. Scale y-1. And we should be able to do that around the 2D cursor, just as we did with everything else. In our case, 2D cursor always horizontal, and its X position is the current keyframe. So we scale it on the Y axis by -1, and it goes all the way up. And now our sphere is stretched in the correct direction. But all the way up there, on the 30th frame, it actually should be 0 rotation. Now let's just copy the entire thing. And actually we can be fine if we delete it and make sure that this happens on the 28th frame. Yep. Now just take this part, copy it, and move it to the right so that we start rotating our ball at around frame 31. So that on the 30th frame, it is in around 0 rotation. Now let's see how it looks. Boing, boing. Yep. Yes. Yes, it will happen. Your ball will indeed rotate with the texture, and if you want your ball with texture to follow this one, that's actually a very good thought that you have got there. I can explain to you how I would approach this. This ball, I would use it as a guideline for the shape of the ball that I want to actually move, to actually show to the end result. And I will create another ball. Let's go with the UV sphere. I will place it right on top of this one, and I will add a shrink wrap modifier to this ball, so that let's hide the animated ball, let's make them, let's parent our newly created ball to this one, and hide the initial ball. But unfortunately it copies the rotation as well, and its rotation is in global coordinates. What we can do, we can apply a constraint to copy rotation. Actually, we can even not parent them. Let's clear the parent with Alt P. Where is everything? Yeah. This ball is hidden. And this one is shrink wrapped about around nothing. Bring it back there to around the center. So we shrink wrap this ball around this ball and copy its location, so that when we move our deformative ball, this ball follows its position and its shape. So as you can see, it tries its best to follow the shape of the ball that we deform. Maybe we should add a little bit more geometry there where it stretches out. Or change the way it tries to shrink wrap to project, maybe? Give it some offset. No, not offset. Should be limit. Yeah, just a little bit of limit. Nope. Alright, should play with that definitely. A little bit more. On the transformed object, its rotation is locked. It is locked. Since we didn't parent it to the sphere, its rotation stays vertical all the time. But this part, where we don't have much geometry, it is intersected by the end of the sphere there. So maybe if we were to use something like a subdivided cube, or just gave a little bit more subdivisions to this thing, doesn't look as good. Or just played around a little bit more with other parameters, then it would copy the geometry of our inner ball. And this ball you can actually rotate however you want. And in the shrink wrap, you can rotate it but it will try to keep the shape. That is a very good idea, actually. Very good exercise you gave us. So that's a very bouncy ball. I'm actually impressed how good it looks. So we have just a little bit of time left. we touched on how to make keyframes, how to make animations, how to open a graph editor, and how to change the interpolation types so that between our keyframes we have data change as we want it to change. Do you understand the logic behind the choice of the interpolation mode for the for the height of the ball? Why do we use quadratic easing? Well, yeah, basically because our position, our height, which we give in the graph, it changes with the second degree, with the polynomial of the second degree. So we have our gravity times time squared over 2 plus some initial velocity time plus initial displacement. This is what we have at each time while we ease into some position. So because we have second degree polynomial there, we choose second degree interpolation for our points. If we had something for the third degree, we would use the third degree, and etc., etc., etc. Yeah. Mm-hmm. Yeah. Yes. I can say you even more. You can save the data that you have generated on the fundamentals of robotics for the location and rotation of your objects and import them into the Blender. But they will look like a bunch of keyframes. You will copy the data for each individual keyframe. Yeah, it will be like dot 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 dot. Yeah, and when you have dots on each individual keyframe, you don't care about interpolation between them because there's nothing between them. You don't have a frame to calculate between them. You just copy the data at this point, you copy the data at this point. Yeah, great. So that's a pretty nice animation that you can repeat at home or on lab. The last thing that I wanted to demonstrate to you today is physics. The physics engine that we have in Blender. It is not as advanced as in some game engines or Houdini, but it is definitely enough to get some job done. So let's create a brick wall. How would you do a brick wall in Blender usually? You just place lots of bricks in the repeating pattern. In modifiers. All right. You can use array to place multiple objects. Or you can do something different. You can press Alt D and say where you want our second object. Use Alt D to make sure that the data of the object is the same, so that we don't make duplicates of the same geometry multiple times. And if we press Shift R, I believe, or what was that? repeat last. That should be Shift R. Okay, let's try again. Shift R, Shift R, Shift R, Shift R. Yep. We easily repeat our multiple actions. Now let's make another piece there and duplicate this entire row upwards. I said duplicate this entire row upwards just a few more times. Yep, looks good. Now, the thing that I probably should have made first, let's select all of those objects and give them some collisions. First of all, we should make them rigid body so that they are affected by gravity, they have some velocity, speed, and weight, and whatever, so that they can be affected by other objects, by force fields like wind, force field, whatever there are else in Blender. And don't forget to give them collisions. As you can see, we only gave that to one of the bricks. To copy these parameters, collision and rigid body, we give these parameters to our one selected object, then select everything else, and just right click, and no way we can't copy to selected. Alright, there is another way. We can go there to object, rigid body, and add active rigid body. It will apply to all selected objects. And if we press space, everything falls to the ground because of, well, gravity. To make a static object in the rigid body, we change it from active to passive, and now it stays in place. It stays where we tell it to stay. Now the entire brick wall falls in place when we press spacebar, when we play animation. To save us from this falling at the beginning, we can go to the frame where everything is stable, select all of our objects, and use where was it? I definitely seen it here. Probably it is apply visual transform. Yes. It will take the current geometry and current positions of all objects that you selected and apply them as the base for the object, so that as you see, we moved to the beginning of the time frame and our bricks stay in the same place where they were during our animation. And, well, here is some funky physics. Or maybe the entire wall is shaking. Well, there is no mortar between the bricks, so I guess that's fine. And it's even better for what we are about to do next. Let's add a wrecking ball, a big ball that we will throw through this brick wall. Let's get some empty object to set as a rotation point. Make it parent to the object so that we can rotate our sphere around this empty, and give the collision and rigid body passive to our sphere. Now insert keyframe in the beginning, insert keyframe a little bit later into the scene. Let's even change the interpolation mode to quadratic and make it ease out so that we start very, very fast. And say that it is animated. Well, now you have explosive walls. Do with that information whatever you want. Animate whatever you want. You can even do the thing called baking. It's actually Blender makes it automatically to not calculate the physics of these things on each frame each time you run the simulation. If you open the rigid body tab of the object, you can see that it has to be somewhere. Probably it was moved to the other place. Yes, a rigid body world. It is in the scene. It basically caches the information about all your displacements and all the rigid body physics that you have going in your scene. And it runs the first time you make something, you animate something. And so let's, for now, delete all bakes. And let's, in our dope sheet, no, not dope sheet, timeline, set the end of animation a little bit further to see how bricks are falling. And you can see down there a little brown progress bar. The bright brown is already cached and baked physics. Everything that is black, if we drop our timeline somewhere in the middle, it doesn't give us anything because it doesn't know how our objects behaved before that. Because to calculate where our objects should be there, we should know where every brick was the frame before. So we need to calculate this entire thing. We can say a Blender to just bake everything. It will quickly go through the entire timeline. And now you can run it at any point in time. Select whatever point you want. Also, as you can see, it created a very good, dynamic, probably I would say even realistic, how to say it, composition. Yes. And you can use this process to create, for example, a wall of the broken castle. I can just get rid of this thing. I can get rid of the bricks that has fallen off the scene. Place a camera around there, like here. And voila, we have a good broken wall as a background for something, or as a wall of a house that has been destroyed or decayed over time. And that is the time for our lecture. So let's have a little break before the lab. And on the lab, I would propose to you to make. Do you know the marble machine? What is marble machine? Well, marbles in English are this little marble or glass balls, and a marble machine is a machine that lifts this ball up, and from up here it goes in a very intricate, like a roller coaster path down to the bottom, where it goes back up and again to the bottom, back up and again to the bottom. What I would like you to do is to make such a machine, to animate it, and probably you can even try to use physics in what you do. Make your marble at some point go off the rails and drop and break a wall, I don't know. Just to work with animation. And keep in mind that in Blender, almost every number field that you see, and not even number field, can be animated. Even things like visibility of the objects. I can animate that I want to see this plane. Yeah, not viewport, but render. I can animate if I want to see this thing in render at frame 218, or if I don't want to see it on frame 219. It is helpful when you switch between modes for the object. You can have physics pre-baked so that your object moves according to the physics, and at some point, for example, a character catches the object. The moment your character grabs the object, your object is now stuck to the hand. So the easiest way to do that will be to hide the pre-baked physics behaving object and show another object on the very next frame that is now hardly glued to the arm of your character. That will create an illusion that object was moving on the physical trajectory, and then it was caught by your character. You can apply it to the elevator of your marble machine, for example. When your marbles are on the elevator, they are glued to the elevator. When they go off of it, they are unglued and follow the physics. And when they go down to the bottom and they get to the claw of the elevator, they are now, well, back glued to the elevator. If you loop it perfectly, that will be, I don't know, bonus points in karma. Maybe in your next project, you'll see what to do with that. I always like nice looped animations. So for now, let's have a 10 minutes break, and in 6 p.m. we will start our lab, and we will end it at let me check the schedule that we are supposed to have. Yes, we will end it at 7:15. So see you all in 10 minutes, and I will work along with you this time and the next time, I believe. And for the next lecture, we will have geometry nodes. The entire lecture will be dedicated to the geometry nodes because it is a very powerful and complex tool. It in some way resembles shaders, but it is very, very different, but very, very powerful game. So yeah, see you in already 8 minutes. All right. So, uh, let's start with making our marble machines. Do you have any questions maybe on what to do, how to do? If you're just looking at what I'm doing, I can explain every step that I'm taking. If that is how you would want this lab to go. All right. So so far I just sketched out the path for the railings on my marble machine. Then for this curve, I selected that I, I select the object through which it was beveled. So basically, these two circles were taken as basic geometry and extruded upwards along the entire length of this path. It was extruded through the origin point. So the origin point is placed in on the curve, basically, on this curve. And from this curve, we get this geometry stretched throughout the entire curve. This will be our railings. Now, what I will do next, I will see if I can make it a physical object with a rigid body so that our ball can ride on it. For some reason, the ball is getting teleported to the beginning. I see that there is a baked information there. So, but it teleports straight to the 0, 0 coordinate when I add the rigid body. Yeah, I think that I can delete baked information, and now we're talking. Yeah. Let's put the ball where we want it to be, a little bit lower so it doesn't bounce around the place. A little bit higher so it doesn't collide into the path. And just give it physics that you wanted. Fortunately, this thing doesn't have collision, at least it seems. It is fixed. It is disable collisions. Yeah, of course. Well, all right then. Let's just duplicate it and name it as rail collider. This one you will rename to just rail, and rail collider we will transform, and not transform, convert to mesh. And now when it's a fully fleshed out mesh, we can give it collisions. And make it a passive rigid body. Yep. Now it's something. But ball is bouncing off because we are using convex hull. So what this does, it simplifies geometry to some n-gon, to some mesh-like surface that encompass all vertices of this geometry. So in the collision view, it would probably look like a blob of about this shape. But if we change it to the mesh, it will actually use the geometry of the mesh itself. And let's decrease this margin to a very, very low number because it was 4 centimeters, where the diameter of the ball was 3. And probably should do the same for the ball. Uh, 001, make it very small. Oh, that actually looks amazing. I didn't expect it to go all the way through. I expected it to fall off at some point. But, well... guess my engineering intuition was great. Yeah, what did you say? I missed a bit. Yeah. So let's make a circle, extrude it inwards. Maybe we can get away with not so detailed circle. It's like 8 subdivisions, because we will subdivide it later. Extrude it inwards, give it some curvature, so it can hold a ball down. And we will have a magical elevator going right through the middle. We can even make a face there, face there, face there, and extrude the rest of it outwards and make it like a stand. With a little bit of subdivision and a little bit of bevel in front of it. Not so little. Maybe a little bit more. A little bit more. Not this much more. Looks fine. Now let's... yeah, now when I want to plug these cables into this thing, I have some issues, because deforming this will be very troublesome. So I will delete completely this and work back with the copy of my track to put it back where I want it to be. And yeah, as you might have noticed, with the track I can control the rotation of each individual part by selecting in edit mode one node and controlling its tilt. So let's put it inside of this base. Like, let's give the ball a little bit of spin, so it rolls around and around this thing. So about this. Yep. We can only hope and adjust our geometry. Looks good. We'll see. If something goes wrong, we will change the mesh. I still would like to try to see if I can make a rail into a collision surface. Yeah. Unfortunately, it seems that the only option is to make it into a mesh. So let's do that. Convert to mesh, collision, rigid body. Yeah. And remember that in rigid body we need to decrease the collision margin. Oops. Right. Well, that's funny. Also remember to switch it to mesh. Why are you falling off now? You didn't do that before. Yeah. Probably should give collision to this as well. And it falls off into the abyss. Well, that should fix it. Or no. So it falls off around. Yeah. Seems like that. Needs to make a more rapid turn there. So let's save this rail and change this thing. We need more curvature, almost like that. And yeah, I'm sorry for the noises in the background. And just drop it off somewhere there. Not into the wall, but like here. Probably should do. What we can do now, we can duplicate it, convert into mesh, select the mesh, copy it, and here paste it in place. Can we paste? We cannot. Well, in that case, we can just yeah. Can we link it? No. But we can link old rail, object data of old rail to object data of new rail. That way it will inherit its geometry and we can delete the new rail. Yeah. But we will save all the other properties. Now the ball falls off in the middle of the track. Yeah. But centrifugal force, etc. Yeah. Yeah. So here's the issues. When I try to tilt one area, it also tilts the... When I try to tilt the vertex, it tilts the entire... it affects the entire segment. So that is a bit troublesome. But nevertheless, with this geometry, I think we have very good chances of success. So again, convert to mesh. Link object data. Make sure that the active one is the one that we want to copy from. And now, if it doesn't follow there, then it falls off in another place. It is too vertical there. Fair enough. Let's subdivide it, move it a little bit further around. Make it not as tilted. And it's stuck there because the base is a convex hull. Get back to mesh. What? Yeah. Maybe that's because of very high margin there. So high that it's somehow affected. What? Why did it drop? Yeah. Yeah. No. Now that looks promising. Change the bevel a bit because it was massacred by the scale. And outer geometry. Nope, not like that. Smaller arcs. That just should do better. Or alrighty. Maybe increase the bevel a bit. Well, those are the imperfections of the physical engine. We can, yeah, as you have seen, it is quite unreliable. We can probably change the rigid body of this thing to a sphere to get some, maybe a little more better results. But seems like something is pushing it off. Well, it's dynamic, it is not animated, it is active. And where is it? Where is it going? Where did it come from? When did he come from? Where did he go? It gets launched into space for some reason. Even if I disable collision, yeah, because I'm running the same pre-baked area again and again. Let's delete all the bakes. Instead, delete bake. Yes. Rigid body. This one's passive. This one's passive. With the mesh. Very low margin. With the mesh. And very low margin. The sphere. And no margin. Still gets launched into space. But it doesn't even collide. Okay. It thinks that it is inside of something. And the something only ends there. Maybe. No. Does this have a rigid body? Does this have a rigid body? No. Follow the mesh. So it's one of those. What? Okay, the ball has very high margin. Yep. And it falls through the box because there's lots of geometry and it goes crazy calculating all of it. And I applied it all. Well, it's never too late to go back and create it once again from scratch. Now All right. Let's give it, let's create a new object, separate from it, leave it visible only as a wire, wrong one. This one solid, this one wire. And the wire object will be our collider. So we will subdivide it to make it very smooth. I'm making extrusions on the edges to make the subdivision more pushed into the edges. And in the center there, well, let's leave it be. Maybe should select this and extrude them as well a little bit. Yeah. So only this thing we will use as a collider. Now here we add our usual bevel and subdivision surface to make it look nice and clean. With this changed to fetch. Yep. This keeps the, well, not this one. Keeps the rigid body, keeps everything. Bouncy ball. What? Is it because of this? Source, if we say base. Yep. That is good. It doesn't have enough speed to go through this corner, or actually it goes fine, but then it goes to the top, leaks itself from the bottom. Yeah, it happens because it starts to go over the top. Can we try to increase the number of steps to 100? I don't care about performance, I care about quality. Let's get rid of the bounciness here. Just carefully. The tracks just jumps off the track. Why are you doing it, little one? Okay, so let's leave it at 10. And by some miracle, it worked. And since we are only making models, we don't care much about why or how. We can just bake it and keep it at that. Now this thing. Body, mesh, base, no, fine. Margin, very, very little. Yep, that should do. Now let's create a magical elevator that will go at about actually the ball takes too much time to settle in. Let's give it a hole in here. And we shall give it a hole there as well. That should do. Now, this is where we will make our magic. At some point in time, when this ball moves like that, we will hide it. So here it's shown, and here so it moves like that. Here it's shown, here we will hide it. But we will, in the previous frame, create a duplicate of this ball. It gets placed at the very beginning. That's unfortunate, because they push each other out. Get the ball down there. Yep. And here. Actually, let me see. Blender bake physics into keyframes. Can we apply it? Let's try. Didn't do anything. Good. Can we maybe search for it? Bake to keyframes. Yes, that's what we wanted. Bake to keyframes up to 169. Actually, let's go all the way. So now we got what Alexander, I believe, mentioned about. On each individual frame, we have a keyframe. So our ball exactly follows what we are talking it to follow. Now, at some point, where this ball comes almost a stop, let's actually just do there. Delete those keyframes, expand timeline a little bit. And from here, I want the ball to move to its initial position. So let's take this keyframe and duplicate it to around here. So it should be rather fast movement, even faster. Maybe like 3 frames slower. Now go back to the graph editor and work with this part. In this part, I want it to move on the z-axis. So I hide everything but z. Yep. And for this segment, I tell it to make a let's make a back. So it's automatically, yeah, looks pretty good, I suppose. So we can end on this frame, go back to the timeline, 255, and now if we run it, it drops to the bottom, gets a little bit of spin, and boop. Now for the boop, I want this piston that sits there at the bottom throughout the entire time. Here is where boop happens. So here it will fly up with the ball. And then slowly descend into its original position. Boop. Now it's a matter of decoration and rendering something nice. Probably could include a piston into this cylinder, make it like a telescopic rod, or even plug in a rocket engine underneath it. Yeah, Thank you. So I would highly advise you to try something like that at home, to mess around it to your heart's content. You have seen how to make the physics, how to make the physics into animation, and even an example of how to perfectly loop it. On the plate on the bottom, yeah, there are actually two plates. One invisible one, which I used for the collisions, so that the ball doesn't go crazy because of all the collisions. And the base plane, which has just is it no, this one. It has a bevel with very little offset and a subdivision with 2 steps. Actually, maybe 1 step was better because it starts to overlap itself. Actually, we can easily combat it by or not. uh, One moment. So the collisions are applied on the result of the modifiers. It is up to your discretion. You can choose if you want to apply it or not. When we were making a physical ball there, and when it had no keyframes and just physics, on the rigid body tab, we had our mesh, and no, it is not a ball property yet. It is an object property yet. So yes, we have very simplified basic geometry. But for the physics tab, we can choose what type of mesh we want to use. If we want to use a base mesh, the one that we can see in the edit mode, if we want to use a final mesh, or if we want to use a deform. What does that mean? So it only applies a deformation modifiers. It doesn't account for the arrays for bevels, only for the deformations. So by switching it to the final, I believe it was final, yes. We account for the all modifiers that we applied to the invisible guideline that we had there. And our invisible guideline is this very smooth part that will actually be invisible in render. Yes, you are very welcome. Do you have any other questions, maybe? All right, then I probably would want to address another thing, which is shading of this ball. Let's give it some light bluish, a little bit darker metallic material, make it smooth. So if we follow this thing, we can see it rotate. So let's do some scratches on it. Let's do a Musgrave texture first of all, which was removed as a separate node in the version of Blender 4.1, and it migrated under the noise. Give it a small bump using the height of the Musgrave. Smaller bump, about this small. Higher the details, lower the dimension. Now I want it kinda rotate, but it is still very difficult to follow whether it does it or not. Yeah, because of Musgrave it goes a little bit crazy because it is very high definition texture being generated. So let's do something else. Let's do some dents and scratches. Let's go with wave texture. See how it looks. Go with Voronoi. Use the color as rotation and plug it into the wave texture. Will that work? Is the base of that. Looks mighty great. Do you get what happens there? This one even can be deleted. Does the ball rotate during motion? Yes, it does, because when we were rendering physics, it had friction enabled, so it was actually rotating while it was moving. But we could have easily applied zero friction to the base, for example, and the ball would slide as if it was on ice. Sorry that I missed your comment for a little bit. But the question still holds. Do you understand what happens in these 4 nodes? And why we get this result? Can you explain why we get these bands all in the different directions? Yeah, like yes, we generated colors there. Warner generates that. Yeah, continue. Kind of, but not exactly. We have the geometry space of the generated texture coordinates that actually rotates with the ball, as we can see here. But does object work as well? Yes, object works as well. Let's do with the object. But we use this color of the Voronoi texture. Let's bump up the scale. To use it as a rotation. So this mapping works for each individual dot on the surface of the ball. And in this area, all those dots were rotated around the center of the sphere. By some degree, that is basically encoded into the color. The same went for other sector and other sector, but since they're all of different colors, they were rotated to different angles. So if we look at what we have here, this texture coordinate that initially was very smooth and ball-like, so like we had color change in this direction, color change in this direction, in the orientation of the sphere. These islands of texture were rotated to different areas. but we still have some color differentiation from side to side within the sector. So that by doing that, when we plug our thing into the wave texture that initially looks like that, we get a rotation. And let me get the vector math there and multiply by 0 to show you maybe how it affects it in progress, so that in each of the islands we apply a different rotation to the basic coordinate frame that we had. And doing that generates us very different results. So kinda, yeah. If we multiply it by 0, our rotation is multiplied by 0, so we don't apply any rotation. And everything that we had generated on this color is reduced to 0. But when we start to increase this number, can you hear me? Can you see me? I see that I'm reading you lost your network connection, trying to reconnect. Well, on my screen, yeah, you see the screenshot. Well, that's great because Google Meet told me that connection lost, re-established connection, basically. Okay, so let's get back to the business. We increase this value, and we increase the influence of these rotations on the coordinate frame. And we displace the waves. All the waves are displaced at some different coefficients on these different islands. So let's leave it at 1. Increase the scale to about 50. Maybe not 50, but like 30. Then add a noise texture. Noise. Probably should use object texture from back there. Yeah, that's why it was so little. Bump it up to 1,000, maybe 1,500. Now with this noise texture, I use mix color to mix this color with pure white, but use noise texture as a vector. Actually, let's look at the noise texture first. Increase the scale and make just for the looks, let's make a color ramp. Bump it up to about here. Maybe a little bit like that. Reduce the scale a little bit. That should do. A little bit higher scale and larger islands. That should do nicely. Get some scratches, and decrease scale of the islands of random generation. Now we can take this and make islands a bit smaller. Take them and plug them into another bump node. And these bumps we can plug right into the second bump. Are you shaded smooth? You are. And what is wrong with you? Because I plugged it into the height. Yeah. Show me the mighty sphere. A little dented, but not the way I like. Increase the thickness of those things. Probably to about 3 times. Add a little bit distortion. Detail scale. Yeah, that should do. Looks like something. Face offset doesn't do anything. Probably should reduce the size of those islands. Well, that was not the result I was aiming for, but it is a good step in the direction of the procedural scratches. Maybe if I were to invert some of those. No, it now looks like a bump. All right, actually, we have the time of our lecture time. The lecture time has ended. And actually, it's already the lab time that has ended. So you are all free to go. And I would be very glad if you make some works on your own and share your results with me. I think that a lab like that is very interesting to work with, to just mess around and have some fun. And on the next lecture, we will enter the realm of geometry nodes. The thing that allows us to create procedurally generated rocks or trees or even lightnings sparkling throughout your scene. Well, on that note, this is the end of the recording and the end of the meeting. Thank you all for listening to me. It is quite unfortunate that we are getting so few people on the lectures, but I hope that people will see the recordings, and if you do, please type something in the comments so that I can see that I'm working not only for money, but also that you enjoy to learn about Blender, and that the way I'm teaching you is that you like it, and if you don't like it, please tell me what you don't like so that I can get better. Because for me as a 4th-year student, it is a great opportunity to increase my understanding of Blender and get very valuable experience in teaching and communicating with people. So if there is anything I can do for you, please tell me. Mhm. Well, that definitely is possible. I will pitch this idea to Potemkin, and we will see how that works. Yeah. Thank you for attending the lecture, and have a good evening. Yeah. Goodbye. Well. Yeah. Thank you. Yeah. Goodbye.